Welcome everybody. I am Matteo Salvarezza. I work at Wolfram Research in the machine learning team. And today I will present a system to implement, to add basically generic custom layers to the neural network framework. So there will be a new net layer in 12.2 called compile layer, which leverages the Wolfram compiler to basically enable general purpose computation inside the framework. So the framework has layers, building blocks, and it's already quite flexible. You can already do quite a lot of things by combining them. But this should basically unlock whatever the new compiler can do. So FunctionCompile. Okay, I'll make a brief introduction about the new compiler, very quick. So we have two compilers in the system, the old one using the function called compile, and the new one from version 12, which is FunctionCompile. And this is what we're going to focus on. So FunctionCompile takes function objects and compiles them to low-level code, producing compile code function objects. As with every compiler, arguments should be typed. There is some type system into play, so I cannot just feed any function to FunctionCompile with a generic argument because it will complain saying that this is not typed. The way FunctionCompile works is you have to specify the types for the arguments. So for example, here I'm creating two functions, one taking a real number and this one taking an integer, both computing, just adding one to the input. And you see here that the compile code function gives you the signature, input and output types. So I obviously have to feed the right input to both functions. So I have to feed a floating point number to FReal and an integer number to fint. Yeah, if I try to do the opposite, the function will complain. Arrays can also be specified. They have to have fixed depth. Both packed arrays and numeric arrays are possible. So for example, this is a compiled function taking two arguments. One is a packed array of real numbers with depth 2, and one is a packed array of real numbers with depth 1. And this is the computation it's going to do. We can create inputs of the correct size, of the correct depth, run them through the function. We can also do the same for numeric arrays. So basically, packed arrays are basically nested lists, or numeric array are actual numeric arrays, which is the object in the language. And so you can also create. You see the signature says numeric array here, and this thing has to take numeric array as input and produce numeric array outputs. So this is what compiled layer we'll be using. More information about the compiler, you can check the compiler talk from yesterday, and also system documentation for these functions here. So let's go to compiled layer. Okay, so basically compiled layer allows a function suitable for compilation for FunctionCompile to be used in the neural network framework. Since in neural networks we deal with arrays, only array arguments are allowed. So either numeric or packed arrays, not scalars basically. Okay, so here I have defined a function which is suitable for compilation. I did not compile this function. So this is an ordinary function object still. This is what I'm going to pass to compile layer to create a layer out of this function. So what happens under the hood is that compile layer will compile this function using FunctionCompile with some internal settings suitable for usage in the framework. So this triggers compilation, and then we build the layer and give us the compiled layer. Compilation is still quite slow, but it will improve in the future. This is probably now, not sure why it's taking. Okay. So that's it. So one important comment to make, one important limitation of compiled layer is that in 12.2, only function taking a single input will be allowed. For multiple input and output layer ports, they will be added in future versions. Okay, so let's start playing with compiled layer. So one interesting aspect is the shape inference. So basically, depending on the function input depth, which is in the signature, and the layer input depth, which is specified layer construction time, compiled layer can interpret the function as either taking a single example as input or a batch of examples as input. So for example, if I define a depth3 function, there's a 3 here, and a depth3 layer, because I specify an input of depth3, then the function is said, we can call it unbatched, which means compiled layer interprets this function as acting on single examples. So this is what you would normally expect, basically. Once the layer is created, you will see that, yeah, its input shape will be 2, 3, 4, and the output shape is 2, 4. So this shape here was filled by just running this function under the hood and see what the shape of the output is. Okay, so basically, in this case, it means that when given a single example of shape 2, 3, 4, this function is just run on the example. But when the layer is given a batch of examples, the function is mapped over the batch. So here I'm defining a single example of shape 2, 3, 4, and then a batch of 5 examples. And this is a generic feature of the neural network framework. Layer can work on objects of both, like both on the, you can give both this and this thing as input to the layer. And we see that the dimensions, in this case, are 2, 4, which is what the layer is telling you. And in the batch case, is a batch of 5 outputs with length 2, 4, because we have put 5 examples in input. Okay, so this is what you would normally expect. The extra thing is that if the depth of the function is 1 more than the depth of the layer, then the function is said to be batched, which means the layer interprets it as running on batches of examples. So in this case, function depth is still 3, layer rank is 2. This will now produce an array of length 4, and the input will be rank 2. What this means is that when this layer is given a batch of examples, this function is evaluated once on the full batch. It's not mapped over the batch. When you give a single example to the layer, on the other hand, the function is evaluated over basically a batch with batch size 1. And everything works again as expected. It's basically everything is depth 1 minus 1 with respect to this case. Okay, so why does this exist? This exists because batch mode can be useful for faster processing. Sometimes you prefer to have this function having the full batch under control, or basically besides speed, is useful for batch processing. So sometimes you do want basically different elements of the batch to interact with each other in neural networks. For example, if you want to do a variety of batch normalization layer, this is a layer that normalizes its examples over the batch. So it needs to have access to the entire batch. You cannot map it over something. Okay. Okay, so a few words about numeric types. So the compiler type system has several real and integer types. Most of them are for numeric array. You have 32 bits real and 64 bits real, and then you get many integer types, both signed and unsigned, with various bit depths, plus machine integer and machine refactor array. So yeah, basically you can play around with this type system. You can create functions which take numeric array of some type and produce numeric array of other types. and you have to respect those strict specifications when running the compiled function. On the other hand, the neural network framework does not have all this granularity of types. We don't distinguish between bit depths, for example, but we do distinguish between real and integers. And so basically what happens is that type information is transferred from the function signature to the layer port types. So here, for example, I'm taking a function which takes a real and then takes the floor of it. So the compiler recognizes this, and so decides that the output type must be an integer type because I'm rounding it. And if we feed this function to the compiled layer, then this will also be reflected on the integers being here. So vector size 5 in the framework means that it's reals. If you don't see anything, it's reals. If you see integers, then it's integer. And so, yeah, this information is transferred over the framework. Okay, this is the last and most complicated part, training. So currently, in order to be used in NetTrain, compile layer needs an additional function to be defined, which is function defining its backward pass on gradient propagation. So let's take a random function here, doing some random complicated computation, and create a net using a compiled layer created from this function and a learnable layer, which is an array inside it. So this net chain. If you try to train this network, training fails because the framework tells us that the net contains one or more compiled layer with no gradient propagating function. For the same reasons, gradients also cannot be computed. So in the framework, you can add this property specification to compute gradients, but this doesn't work if you don't have a backward propagating function. So what is this backward propagating function? For those not familiar with neural networks, basically neural networks operators, neural network layers do two separate computations, basically. We have a forward propagation, which just computes, takes an input and applies a function computing the output, which is everything we've discussed so far. And then we have a backward propagation, which is used to compute gradients across the network, which is what's needed for optimization, for training, of course. So in backward propagation, you start from the inputs, you reuse the inputs, and you also start from a gradient coming from outside. So this is, you can think of this as relative to a single layer, to a single building block in the network. Every layer receives an output gradient from the layer which comes after it. That's why it's called backward. Okay, so this is the input of the backward propagation, and what the backward propagation computes is basically the dot product between this output gradient coming from the outside and the Jacobian of the forward function with respect to its input. Okay, so this is what the backward function has to compute. So let's add this function. Let's implement this. Turns out that for the language symbolic differentiation capabilities are quite useful to implement these functions. So let's try basically to compute these things symbolically. Instead, the alternative is working it out on pen and paper, basically, or in your head. Okay, so we create a symbolic input, for example, vector of length 5, and we run f, which is our forward function. So this function, we run f on this input and we get this output, which is a vector of size 4. The Jacobian is just the symbolic derivative of the output with respect to the input. So we can use the d function, which does symbolic differentiation, and we have our nice Jacobian matrix of dimensions 8, 5. So output size, input size. Okay, so last step is to take the dot product of this matrix with an output gradient, which I'm defining here, and this is the result. So basically now what we want is we want to create a function which computes this thing. And this is it. This is a slightly optimized implementation of this. So we got our grading function. Okay, so notice that, as I said, the backward pass needs two inputs, the actual input from the forward and the output gradient, but the function I've just defined takes three inputs. It takes the input, it takes the output gradient, but it also takes the output. So what is this thing? This is basically this quantity, which was pre-computed from the previous forward pass. And the reason why this is made accessible to this function is that, in general, sometimes the gradient propagation output. So you can think as, for example, the exponential function. So the derivative of the exponential function is the exponential itself. So if you were to, implement a gradient propagating function for the exponential, which you don't need to do because the framework can do the exponentiation natively, but this is just for the sake of argument, you would just reuse this output. But in general, it's something that it can be useful to have. So this picture kind of summarizes everything. So everything happens, every time you want to, sometimes you just want to repeat the forward pass. So you take the input, you give it to the forward function, you have the output, and you're done. But if you're doing training or if you're propagating gradient, after you've done this step, you have to do this step. So in the backward pass, you see this backward function blob has three inputs. It uses the actual input from the forward. It uses the output pre-computed by the forward, which can optionally be reused to save time. And it uses the output gradient, which comes from the output. So this is our OI vector. And this produces the input gradient. I got two questions. Yeah, so automatic differentiation, I will come to that later. How does compare relate to function layer? Good question. So function layer basically, how much slower is function layer? Well, it depends. You actually expect function layer to be faster usually. And the reason is that function layer compiles directly to, basically function layer takes top level Wolfram language code and translates it to net graphs. That's what it does. Net graphs means that, in our framework, a net graph translates to an MXNet graph. And so it will natively use MXNet primitives, which you expect, and they generally are, to be very, very optimized. While with function layer, you have potentially way more flexibility because you have, you can do everything the compiler can do, which in the long run means you can do everything the language will be able to do. But you will not have a super optimized implementation, created by a human in native C++ code. So this is the difference. Function layer actually still translates to every layer that we are currently using in the framework already. So as of now, it's just a convenience, basically, to write net graph more easily. Compiled layer is actually more flexible and can do more things. Yeah, in the future, they will probably merge, which means that function layer, which could become net function, will be able to translate top-level Wolfram language code either in net graphs, but it can also compile some intermediate pieces into compiled layers. So they will merge at some point. Okay. Okay, so now that we have our gradient function, we can just add it to the layer. So it's just the second argument here. And with this, we are now equipped to do training and to do gradient computation. Creation takes a little bit more because it has to compile 2 functions now. I can create this network, and now gradient computation works, and training also can start. Okay, so that's it. This is everything I wanted to show. So for future development, so this is compile layer is promising, but it's still quite limited. What has to happen is multiple input-output ports. So create a compiled layer with 2 input ports from a function with 2 arguments. So right now, if I try to do it, layer function must take 1 type array as input. This is very important to have generic computation, of course. Learnable arrays. So it will be possible to create a compiled layer containing learnable arrays inside it, just like convolution or linear layers. Or we're still not sure how this is going to happen. Alternative option will be that through this multi-input mechanism, you will basically be able to make a learnable compiled layer by using a combination of multiple inputs and net array layer, which is what was previously called constant array layer, acting as holding the learnable arrays for the layer. And this is one of the questions, automatic differentiation. So basically, what we are able to do in the near future will be to automatically generate the gradient propagating function from the forward function without asking the user to implement it. And this will use the functionality which has been mentioned in the question, which is compiled to derivative code function. It's actually compiled to a joint code function. But yes, well, for 12.2, you might be able to create you might be able to create the backward propagating function yourself using automatic differentiation, but it will not be automatic. So you will still have to plug manually the function into the layer. But in the future, everything will be, it will try to do it automatically, so it will be much nicer. Okay, so this is, that's the end of the presentation. If anybody has questions, we still got 5 minutes. Is loop and if supported? Yes. As far as it's supported in FunctionCompile, it is. The only limitation is that you cannot produce, for example, in an if with generic general purpose code, you can produce very, very different results in the 2 branches of the if. While in neural networks, you have to produce arrays, of course, and you have to produce arrays of the same shape. So because you cannot have, a layer like compiled layer or anything having an undefined output size here, which can be 2, 3, 3 sometimes, but some other times it can be a list of length 10. You cannot have that. So output shape and also a number of outputs must be the same, but then you can have it inside, yes. Will this allow user-defined net encoders decoders? Well, it doesn't need to, because you can already do it. There is the net encoder function, and you can have a function here. Net encoders and you can do the same for decoders. Basically, the encoders and decoders don't need this complicated mechanism going to FunctionCompile because they are not really part of the network. They are sort of outside the network. They have pre-processing. So we had this since quite a long time already. So yeah. Will it train on GPU? So it will technically work if you do target device GPU, but will technically not run on GPU as of now. It will copy back to CPU, run on CPU, and go back to GPU. And this is because the compiler currently is not able to compile to GPU. But it will in the future. So at some point, it will also run natively on GPU, which means basically there are no gains using this on GPU. And if you train a network with a compiled layer on GPU, the compiled layer is likely to be a bottleneck. Unless the compiled layer is very simple. If the compiled layer is very simple computation, and you have a lot of heavyweight convolution layers on the GPU, then it will not be a bottleneck. But it's more likely to be a bottleneck because it runs on CPU, and you also have to wait for data copy from GPU back to CPU to get the compiled layer to work and transferring the data back to GPU. Will nets including these infer on Raspberry Pi? I think so. I'm not exactly sure if the compiler, I'm not going to make the promise that the compiler can compile on ARM, but I would guess so. Honestly, I didn't try. But if FunctionCompile works on Raspberry Pi, then this works on Raspberry Pi. If there is a random number used in compile layer, can we keep it the same in both forward and backward? This is a tough question. So the question, I think, it means if you generate, okay, so yeah, here's a way to see this. If you generate the number inside the compiled layer, there is no way to keep it. But it can be possible. This is interesting. It can be made possible by using the yeah, at least theoretically, you can use MXNet as functionality to do that. Let's say this. It has auxiliary arrays, which are, for example, used by batch normalization layer. Problem is we don't have an analog of that on top level, so it might be hard to add. But it's definitely something interesting that we should look into. One other option is that you generate the random number outside the layer. If you generate the random number outside the layer, then the random number is an input to the layer. And if it's an input to the layer, then you get the same random number in the backward pass because of this. So when you do the backward, you reuse the input. And so if you generate the number outside, you will be able to do it. But you will need multiple input output because you will need the port for the actual input besides the random number, so it will not be possible in 12.2.
Matteo, it looks like you have a couple questions in the Zoom chat too.
Oh, okay.
I'm not sure if you saw those.
Sorry. I stopped looking at those because questions weren't coming.
Yeah, they were going in the Pathable chat.
So is it on the Zoom chat or on?
Yeah, it's under the Zoom controls.
Yes. Okay. Okay, so the first question is a compilation of questions which I've already answered. Okay, no, there are no new questions. Then there is a comment from Roadmap. So yeah, no new questions. Okay, seems there are no more questions. we're going to stop this.